Alright, in this video I'm going to be going over 2021 BC number 5, and this is the differential equation. Okay, they're going to ask you Taylor series question, ask you to do Euler's method, they're going to ask you to do separation of variables. This one's actually pretty straightforward, at least for this year. So, they start off by giving you dy dx is y times x log x. They tell you that f is a solution to that differential equation with f of 1 equals 4, and they tell you that it can be shown that f double prime of 1 is equal to 4, so that's just one less thing for us to worry about. But right now they want us to write the second degree Taylor polynomial for f around x equals 1 and use the Taylor polynomial to approximate the value of f of 2. Well, what I'm going to need, the ingredients for the Taylor polynomial is all the derivatives up to degree 2. So I've got f of 1. I don't have f prime of 1. I have f double prime of 1. So I need f prime of 1. So first I need to find f of 1. Well, f of 1 is, they gave me dy dx, so that's like the next best thing. At the point where x is 1 and y is 4. And that's going to be equal to, all right, well, y is 4 times 1 times the log of 1. And we know that the log of 1 is 0. So I'm going to say that, no, since I've got f prime of 1 equals 0, and I know that the second degree Taylor polynomial is, whoops, just shredded my piece of chalk. It's f of 1 plus f prime of 1 times x minus 1 to the first divided by 1 factorial plus f double prime of 1 divided by 2 factorial times x minus 1 to the 2. So now what I'm going to do is I'm just going to kind of erase the things that I know and replace them with numbers. F of 1, I've got that. That's 4. F prime of 1, I just showed that that was equal to 0. And then f double prime of 1, they told me in the statement of the question, very politely told me that this was 4. Okay, so there's my second degree Taylor polynomial. If I want to approximate f of 2 is going to be approximately equal to whatever I get when I plug in 2 into the second degree Taylor polynomial that I just wrote. And so it's going to be 4 plus 4 over 2 factorial times 2 minus 1 to the second power, and I'm just going to leave it there. Yes, that's 6, but, you know, any amount of time you'd spend looking at that is time you could spend doing a different part of the problem. Okay, so for the second part, they're going to ask me to do Euler's method, so I'll copy the problem. Okay, there it is. So they say, use Euler's method with 2 steps of equal size. They mentioned that in the statement of the question. Equal size starting at x equals 1 to approximate the value of f of 2. So what I'm going to do, just like usual, I'm going to start off by kind of like sketching out my interval. I've got 1. I'm going to 2 with 2 steps of equal size. So my first step will be x equals 1.5. My second step will be x equals 2, and that'll be what I'm going for. So I need 2 tangent lines if I want 2 steps on Euler's method. So my first tangent line, I need a point. And that would be 1, 4, the point that they gave me, x equals 1, f of 1 equals 4. Slope is dy dx. Well, I just showed right around here earlier that dy dx was 0 because it was 4 times 1 times the log of 1, which is 0. Okay. So I've got a point and a slope. I need an equation. So y minus 4 is 0 times x minus 1. It's a little weird, but we can deal with this. So I'm going to approximate f of 1.5. It's going to be 4 plus 0 times 1.5 minus 1. Well, I just know it's going to be 0. And so that's 4. So my new point for my second tangent line is going to be 1.5 and 4. Okay? Because x was 1.5 and f was approximately equal to 4. My slope, I'm going to have to run that through there. And so that'll be 4 times 1.5 times the natural log of 1.5, which I don't know what that is. I don't really need to know. Okay, and I might call that 6 log of 1.5. And now I'm going to write down an equation for the tangent line. So it's y minus 4 is equal to 6 log of 1.5 times x minus 1.5. And I'll be able to plug in x equals 2 and get myself a good approximation. It'll be great. Okay, so yeah, now I'm ready. I'm going to do f of 2 is approximately equal to 4 plus 6 log of 1.5 times, well, when I plug in 2 and I subtract 1.5, I'll have 1/2. It's like, yeah, we could reduce that to a 3. We could also make that 1.5 to the third power. You can even figure out what 1.5 to the third power was, right? But like, you'd be no more right, so I would just recommend stopping here. I did have something else to say about this somehow. What would it have been? There it is. Oh, yeah. Since they said 2 steps of equal size, a good quick check, make sure I did this right. Did I multiply the same number here as I did there? And I did, so, okay, at least I didn't catch an error there. Okay? That's what I got this morning when I did. So, for part C. Part C is going to ask us to find the particular solution using separation of variables. This should be something that's pretty comfortable to you, except for this one's going to require a little bit of extra from that product there. All right, so part C says, find the particular solution y equals f of x to the differential equation dy dx equals y times x log x with initial condition f of 1 equals 4. We can do this. All right, so I'm going to separate my variables. I'm going to divide by y and multiply both sides by dx. So I'll have 1 over y dy equals x times the natural log of x dx. And then I'm going to anti-differentiate both sides. Okay. And this one will be, you know, kind of easy enough. Log absolute value of y. We've done these before. This is not going to be so easy. I'm going to get a different color and kind of work off to the side on this. Maybe I'll grab blue. And I'll do my UDV off over here. Okay. So I think to myself, this is a product. And I'm not seeing something that's the derivative of something else, so it's not going to be UDU. It's going to be UDV. And so UDV, I late log before algebra, so I'm going to let u equal log of x and dv be x dx. Okay? Then du is going to be 1 over x dx. And v is 1/2 x squared. And you know that the integral of u dv is u times v minus the integral of v du. So the integral of, what is it, log x times x dx is going to be 1/2 x squared log of x minus the integral of v du would be 1/2 of x squared divided by x. So 1/2 x to the first. Okay, that's going to be 1/4 of x squared. So 1/2 x squared log x minus 1/4 x squared. You know, plus c, I guess. So I'll copy that on over here. Yes, I'm just going to copy that right over here. 1/2 x squared log x minus 1/4 x squared plus c. All right, and so I don't think this is actually going to be too hard to solve for y, but something about this makes me feel like f of 1 equals 4. Yeah, it's not going to go that well if I take e to both sides power. I want to take e to the 0 power to most easily find the value of c, so I think what I'm going to do is I'm going to actually just plug in here right now. So log of the absolute value of 4, so log of 4 is equal to, I'm going to plug in 1 for x, so 1/2 times 1 times log of 1 is 0, minus 1/4, plus c. Okay, I suppose that means that c is 1/4 plus the log of 4. Okay, and so then I'll just have, well, let's see, y equals plus or minus e to the, all of this, plus 1/4 plus log of 4. Now, if I wait till this point to try to figure out my c, usually the c will kind of dictate whether I'm taking the plus or the minus. But in this case, I have to make that decision based on the initial condition. But if we think about y is a positive number, that means it has to be this positive number in order to fit the initial condition. So it's going to be, well, here's my y of x. Okay, that's y equals some function of x. And that was not the best separation of variables of all time, but we were able to separate and solve for it. So there it is. And that was number 5.